So we're going to talk about a little bit about putting bits into files, a little bit more. I feel like I need to give you a little bit more detail about how that's going to work. And then we're going to go into an introduction to graph theory, which is really important to the Huffman encoding, which relies on so-called binary trees, which are graphs, a particular kind of graph. And we'll spend most of the time talking about the vocabulary of graphs and traversals of graphs and so forth. And I think maybe by Monday or Wednesday of next week we can start talking about Huffman compression. All right. So any questions before I get rolling? Well, then, without further ado, let's talk about, you'll recall here that I'm asking you to write a bitstream class, and in that bitstream class, we have two member functions that are really important. There's putting a bit and getting a bit, these two guys. The other two really can be built out of these first two. So I'm not really worried about the other two. I want to talk about putbit and getBit. In particular, I want to sketch putbit. So putbit, if you'll remember, takes a single argument. And writes it to the output file. But we know secretly that it's not writing it to the output file. It's writing it to a byte buffer, which, when it fills, will be sent out to the file. So if you look at this header file, you'll see there's obit pause and ibit pause. Obit pause is the output bit position, and put bit is responsible for keeping that guy updated. So I'm going to, let's talk a little bit about the bytes in my program, and then I'll talk about what some of your what some flexibility you might have would be. Here's a byte. I'm going to choose. I'm writing this byte in big end notation, big endian notation. Big endian means that it goes from left to right, is most significant to least significant. So when you see the phrase big endian, it means that left to right is most significant to least significant. This is how we normally write our decimal numbers. 512 is a big endian convention, right? 5 is the most significant digit, 2 is the least significant digit. That's called big endian in computer science. Big endian for a byte means that this is 2 to the 7th down to 2 to the 0. Okay? So our binary numbers are going to look like that. I chose in my putbit program to write from left to right across the byte. Go ahead.
x86 is a little weird, right?
It is, yes. So I chose to write left to right. All right. So my byte buffer, my bit pause is going to start out. Is going to start out at 7. And then every time I write, we do obit pos minus minus. All right, so that's my little bookkeeper that keeps track of what I've done, and that's a member of the class. So my put bit, lots of different ways you can do this, but is going to take a single argument b, which stands for bit, and it's either 0 or 1, and that's an integer. I mean, if you wanted, you could make it a Boolean, but it doesn't really matter. I suppose if you were going to have lots of, if memory was an issue, then you might make it a Boolean, because then it would be a character instead of 4 bytes, but it's not a big deal. This b is going to be 0 or 1. When I get inside, the way that I've written mine, when I get inside, I'm going to check to see if I need to flush. So given how I've described my setup, what is the flush condition?
If obit is negative.
Yeah. So the very first thing I have in my put bit is if obit pos is negative, then I'm going to flush. And it's flush's job to do two things. What are they?
Flush and to reset obit pos.
Yes. And I don't know if I put that in my comment. Flush. So write out the most recent byte buffer. And it's also flush's job to reset. And resetting obit pos means doing what? In my case, setting it to 7. Tons of variations on this theme, as you might imagine. For example, you could set obit pos to 8, right, and decrement it before you start using it. And if obit pos is 0, then right, or you could count up. You could go from 0 up to 7. And if obit pos is 8, then reset it back down to 0. Lots of different ways to do this. So that's what I've chosen to do. And I'm going to get, what I'd like to do is set the obit pos bit to B. So whatever obit pos is sitting at, whatever position it's pointing at, I want to set that bit to B. So I have to get a mask, and as is typical with masks, we can set it to 1 if we want the thing in the far right.
We want that to be an unsigned character, right?
Yeah, and I can't remember if I made it part of my class or not, but just to make sure, yeah, let's do that.
Oh, okay. Wait.
But just to remind everybody. So there's an unsigned character mask. We're going to set it equal to 1. Okay, so what do we need to do here? We need to put that 1 in the right location. How do we do that? Yeah, the shift operators, remember those? Yeah, so that would be mask equals mask obit pos. Let me just make sure I'm thinking about that correctly.
So then we have to have, I mean, we could just adjust it there, but it would be most convenient to have obit pos start at 7 and go to 0 because of this.
Not really, because you could just flip the, you could set mask equal to 8, 8? No, not 8.
255.
255, yeah.
No, 128. So just
Yeah, 128. So yeah, there's lots of different ways to do it, but certainly this seems conceptually easy. So every one of these steps can be done in a million different ways. And yes, 128 is going to get 2 to the 7th set to 1, and everything else will be 0. Is this doing the right thing? Let me think about it for a second. So it starts out with it's in 0, and I'm going to slide it at most over to 7, right? Over to position 7. So that makes sense to me. Okay, what's next? We want to set this bit position to the value B. How am I going to pull that off?
Now we have 2 cases.
Why?
It can be 0 or it can be 1.
It can be 0 or it can be 1, and the way of accomplishing that are different. So if C, then not C, B. I had C in my notes. If B, then byte buffer.
0 is true and 1 is false.
Yeah. Byte buffer is equal to byte buffer.
What happens if, I mean, this really needs to be a programmer error as opposed to user error, but what would happen if you did it if some other int? So like if 2.
Oh, that's true. Non-zero is true, 0 is false. Yeah, so
even negative.
So you want to be careful, yeah. Essentially, when that if statement executes, it just goes and looks at the memory there, and it looks for any set bits. And if there's a set bit there, then it's true, no matter what the memory is. So if B is 1, that's non-zero, so that's true. So we're going to do this. Byte buffer equals byte buffer or mask. Does that work? You've got zeros everywhere in the mask except in the O-bit pause position, which is 1. No matter what is in the corresponding position of the byte buffer, after this OR is done, that's going to be a 1. Everything else is going to be unchanged, and we're done. Else? Else byte buffer is byte buffer and not mask. Remember what not mask does?
It switches.
All the bits get flipped. So all the zeros become 1s, all the 1s become zeros, and this then you do ANDing, and it'll make sure that the O-bit pause bit is 0.
And all the other ones will stay the same.
All the other ones will stay the same. Not quite done yet?
O-bit pause plus pause.
Minus minus in my case, but yes. Question. Does flush need to do anything to the byte buffer other than write it out? For example, does it need to clear the byte buffer?
You could make a new one.
Could make a new one. You could set it to 0. But is it necessary to do anything to the byte buffer?
I'm just going to overrun it.
It's literally going to be overwritten the way that we've designed this thing. At the end, if you care, at the end, when your program is exited and you've only written half of the byte buffer and then you flush it out, if you want zeros in there, then go ahead and throw some zeros in there. But if you don't, you should recognize that the last scraps of the byte buffer are really are scraps, or meaningless if you write it out. But that's fine. Okay?
Fine.
It is fine.
So if this is the way that, so last class we were talking about doing a like word of a length that didn't divide exactly the number of bits that
Yes.
you had. Does that mean that because we're not resetting the byte buffer, if we run it,
If you run it too far,
yeah, that we could end up with slightly different responses?
yeah. Now for us, it's not going to be a problem. There's no danger of running past the meaningful bits, because in the Huffman code, it's really kind of interesting. In the Huffman code, what you do is you throw in an extra fake character called end of file, and you encode that in with all the rest of the characters. And when you're reading bits, if you read bits and you end up with the end of file code, you're done. You stop. And so that is going to prevent you from ever going past into meaningless bits. So it's not something that we have to worry about, but it is something to think about. The end of file bit is sort of, the end of file character that we're going to use is a little bit irksome, and it's why, it's the whole reason we need these other guys. GetInt and putInt in b-bit representation. I'll talk more about it later, but when you throw in that extra fake end of file character, it makes it so that you have 257 possible characters instead of 256 possible characters, and so you need 9 bits to fully represent them, and there's no way around it. There's literally no way around it, and you'll see why when we get to that point.
How is it? So the end of file is actually just like outside of the normal ASCII?
Right, because we want to be able to encode all possible bytes. 0 to 255. How many different bytes are there? There's 256.
Yeah.
We need some kind of signal in the compressed file, some kind of signal to tell us that we've reached the end of the compressed file. And the only way to do that is to introduce this fake 257th byte.
Can you also just decide, well, no one actually wants to use this ASCII character anyway?
No, because our compression program is going to compress binary files as well as ASCII files, right? Remember when I showed you, like, I showed you that really gobbledygook kind of file?
Yeah.
That file consists of more than just the ASCII character sets. It has just totally all the different bytes are represented in there. And we want to be able to compress all the different bytes. So if we excluded one of them, reserved it as an end of file, then we wouldn't be able to make running a.outs, for example. We wouldn't be able to compress a.out, for example. Because to build a functioning a.out, you need to represent all possible bytes. So yeah, you're kind of stuck. So there's a put bit. Here's a question. A file is a FIFO. Anybody know what a FIFO is? Is a first in, first out. And our bit stream, which is writing to files, needs to preserve the FIFO-ness. Which means, let's talk about this now. I've got a byte, and I'm writing into it like this. Here's my direction. And now I take it and I dump it out to a file. And let's say I read it in. which, in the top picture here, which of the bits gets written to the file first in my scheme? The leftmost bit gets written first. So when I'm reading out of the file, which of the bits needs to be read first by get bit? The leftmost. So when you're writing this guy, so here's put bit. Get bit needs to work in coordination or in consistently with get bit needs to work in the same direction. So if your obit pos goes 7 6 5 4 3 2 1 0, your get bit, your ibit pos needs to do the same thing, so that the first bit written is the first bit read. Everybody with me on that? Now, the bytes themselves, right? As the bytes are written to the file and read to the file, that's just regular old C. Putting a byte out to a file, reading a byte into a file, from a file. That's FIFO, right? You don't have to worry about that aspect of it. The first byte that you write out is going to be the first byte that you read in. That's FIFO. This guy is under your control. You need to make sure you're consistent with FIFO, writing in the same direction and reading in the same direction across the byte. But you're free, unlike what I did, you're free to start here and go to the left, as long as you start here on get bit and go to the left. So the direction doesn't matter as long as you're consistent with it in both put and get. Is that clear to everybody? So if the first bit you write in your byte buffer is this guy, then the first bit you read from a new byte buffer has to be that guy. And that'll preserve FIFO. This thing is just really difficult to debug, so you've got to... the way that I suggest debugging is kind of the stuff that I was doing in class last time. Writing ASCII characters and then reading them back as numbers and partitioning them into like different bite-sized chunks and making sure, like, basically getting out a piece of scrap paper and making sure that that you can partition these things in different bite-sized chunks and get the correct numbers out. So it's going to be really scrap paper, a lot of scrap paper, designing and testing this thing. I think that's all I'm going to say about Bitstream for the moment, unless people come in with specific questions. Luke?
I just have a question about what we're going to be using to read and write the bits to a file. Just the that side, but at least I don't think I've ever.
Right. There's a. Oh gosh, I think it's .put and .get will just write characters. So, in fact, let me just double check that for you.
So we're writing to the file in terms of characters?
Yes.
Oh, interesting. So it's just going to be like gobbledygook.
Right. You're going to get a byte. And that's why I encourage you to work in ASCII, because then you can actually open it up in VI and make sense of it. Right? Like, you know what an A is, you know what its value is, and it's much more difficult to work on characters that are not visible or don't play well with the terminal. Yeah, let me just remind myself what I did. So I'm going to go check my flush. There are a couple different ways, and that's why I want to make sure that I'm giving you good advice. Looks like I did write a Looks like just the regular old insertion function is going to work. So I didn't use put or get. But put and get can write also. So if you want to do that.
I was just wondering, do we or will we have a specific destructor for this?
I didn't ask for one, but you'll notice I put one in there. So
Okay. Like
Yeah.
when would that be useful?
when it essentially, if you don't want to manually call flush,
Right.
you can let C++ call the destructor which has flush in it.
That was kind of what
Yeah.
I was gonna be
Yep.
getting at.
You mean at the end of the program?
When the bit stream passes out of scope, it will flush automatically. It'll call the destructor. All right, let's talk a little graph theory. It's an unfortunate name because at this point in your careers, when you think of graph, you think of an XY coordinate system and x and f of x and all that sort of stuff. And that's certainly a meaning of the word graph. The meaning of the meaning of graph that we're going to use in here is completely unrelated to that picture that you have in your head. A graph is a collection of vertices and edges connecting those vertices. So I can just write a little dot right there. That's a graph. It's not very interesting, but it's a graph. Or I can write a dot and another dot, and I can draw a line between the two of them. And that's a graph. It has two nodes. These are also called nodes. Two nodes and one edge. This guy has one node and no edges. And it goes on from there, right? I mean, I can have as many of these things of these nodes as I want and as many different edges as I want. Something like that. And you'll often have crossings like that, but they don't mean anything in graph theory. It's really just a matter of convenience. It's hard to write these things on pieces of paper, so sometimes edges will cross. But unless there's a solid dot at the crossing, it doesn't mean anything. The edge is really just saying, yes, I can get from this point to this point along this edge. The intersection is meaningless. Okay, let's talk about this graph right here. This graph has what's called a cycle in it. So I can get from here to here to here and back. That's a closed path. Also called a cycle. And I guess the idea is that you only traverse each edge once. The reason I say that is because there are no cycles here. And and I want to eliminate the possibility of you going out to here and then back. All right, if your graph let me do one more before I go there. Now, if I put all this in a box, that's a graph. But it's not connected. Because I can't get to that node that's out there by following edges. I could even have this guy, right? And these two guys together are a graph, but they're not connected. Because there's no path from say, this guy to this guy. All right, a tree is a connected graph with no cycles. The thing inside this box is a tree. The thing inside this box is a tree. The thing inside this box is a tree. So the first one is an empty tree. Second one is sort of a trivial tree, and then from there on, you actually have honest-to-goodness trees. Here's a typical tree. So does everybody see how this is connected? I can get from every node to every other node by following edges in the graph. Yeah, nothing's disconnected. And there are no cycles. This is pretty much a generic tree. That they all pretty much look like that. You'll notice, however, I didn't... like this node has 2 branches leading off of it, and this node has 3 branches leading off of it. So there's, right, you can have as many edges coming into a particular node as you like. Yeah?
If you're running a binary tree, would it be useful to keep track of the binary like opposite? So like have the pairs connected, I guess, if you will, even though then technically it wouldn't be a tree.
There are so many variations. Yes, I mean, certainly if you want to know who your siblings are, then you should set up some sort of connection between them. If it's important for you to be able to know who your siblings are without going to the parent, then absolutely. This guy at the top is called the root. But that's an arbitrary designation. Yes. Any one of these nodes could be a root node. And it's really just by fiat. You know, you're the person building the tree, you get to pick the root. There's the root. Typically we put the root at the top and have the tree flow down from the root. So that's a little bit just messing up the metaphor. But to keep the metaphor going, this is a leaf.
So is a leaf a like terminal node that is not the root?
Yeah, let me describe a little bit how this works. So I have a whole list of vocabulary that I want to get through here. So let me, just by example here, I'm going to call this root node R, I guess. And I'll call this A. And we'll call this B. So R is the parent of A and B. A is a child of R. What else do we want to talk about? B is a child of R and a sibling of A. And I give these as specific examples, but they generalize. So if I go down here and I talk about, say, C here, C is a child of A. It's not a child of B.
Do we go grandchild then?
You can go grandchild, but usually past child you just talk about descendants, and past parent you talk about ancestors. And I'm leaving out a lot of very careful, technical, mathematical definitions here. I'm speaking very loosely, and I'm talking about this by example rather than by laying out a whole bunch of formal definitions in front of you. That said, I want you to read David's chapter 5 and look at those formal definitions. Yona?
Do trees ever have directed edges?
Yes, and they're called directed graphs. We're not really interested in directed graphs right now. They are an important aspect of computer science, but not something that we're going to really talk about much in this class. So in our class, I can travel in either direction along a node, along an edge. But in a directed graph, it's you can only travel in the direction indicated.
So like a linked list that has no backwards, but
That's a good example, right? So a linked list is a directed graph from the head to the end.
it's also a tree.
But a doubly linked list is just a graph. And in order to go back and forth, we need two pointers, right? One to go, one for next, and one for prev. Let me keep going with my vocabulary here. Let's say that C is a descendant of R. And R is an ancestor of C. R is also an ancestor of A and B, but more specifically, it's a parent.
So the root will be
Ancestor of everything, yes. But do you see how the designation root is kind of arbitrary, right? If I grabbed a hold of C and kind of picked it up, right, and let everything else sort of sag below, then there's nothing really special about C versus R being the root. It does change some of the statistics about the graph, which I'm going to introduce right now. For example, let's talk about the depth of a node. So the depth, if I could write, of C is 2. So how many edges do I have to cross to get from the root down to C? 2 edges. So the depth is 2. On the other hand, if I made C root, what would the okay, before I go there, what's the maximum depth of the whole tree? 3. Down to that node that I have labeled as leaf. It takes 3 edges to get there, and there's no other node in the tree that's deeper than that, right? So the depth of the tree is 3. If instead I chose C as the root, what would the depth of the tree be? 1, 2, 3, 4, 5. Yes, 5. So your designation of root does have an impact on some of these descriptors. A leaf has no children. root has no parent. There's only one root, and there are potentially lots of leaves. Okay?
So within a given tree, if you were to arbitrarily, choose different roots, would you always have within one the same number of leaves? So either like n or n minus 1.
You're going to, I think, for example, if I take C and make it root, I lost a leaf.
Yeah. But you can never lose more.
I can't lose more than one. Yeah, I think that's a fair statement. Yeah. Yep. And if I take an interior node, same number of leaves. Yeah. So an interior node is a non-leaf node.
Would the root be an interior node?
That's a good question. I don't know how David has it defined. It's not something that I use a whole lot, but let's just guess that it is. And then I'll put root question mark here, and we can check David's notes and see how he defines it. David's the graph theorist in the department. I only do it as is necessary for data structures. All right. Let's see. We've got parent. We've got sibling. Did I say sibling? Yeah. No? I mentioned it.
Yeah, he is a child of R and a sibling of A.
There you go. Good. Ancestor, descendant, subtree. Subtree. So you take one node and you say, let this be the root of the subtree, and take all of its descendants. So I can come up here and say B, this is the subtree at B.
You have a trivial subtree as well, but
All the leaves are trivial subtrees, for example.
the entire tree as well.
And the whole tree, I guess, is, yeah, you would call that a subtree of itself. Yeah. In fact, if you read David's notes, he defines trees in a recursive way using the subtree idea. So he defines it a little bit differently than I did, which was, for me, it was a connected graph with no cycles. For David, he does it recursively, and it's clever. You should definitely read it. Okay, a binary tree. Each node has at most 2 children. And a complete binary tree Shoot, can I do this yet? I don't think I can do that yet. I'll draw one for you. So here's a binary tree. But it's not a complete binary tree. To make this complete, and there's a somewhat arbitrary sense to this. So this is binary tree, but not complete. To make this guy complete, what I have to do, and I'll draw in red the stuff that I have to add to make this complete. Drawing trees is really hard. Am I there yet? Nope, I need that guy. And then I gotta do this, 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 this. I can't do it. I'm out of space.
All the leaves are of the same depth.
I've got to fill it all the way down, yeah, so that I fill this whole level. And I've got to fill this down too. But I can leave this open.
Oh, because it goes from left to right.
Yeah. So it's complete if all the nodes at a single depth from left to right are filled. So all the nodes above at depth n. So, and they just have to be complete at depth n. So you can have this open spot in the lower right part of the binary tree.
That must be one single node that was not there, right?
No, I can kind of back up sort of as far into this as I want. Let me go back to black here. I can have as sort of this whole, and that's still complete. As long as I I just fill across like this. The siblings from left to right are filled and there are no gaps. It's not a really big deal, but it's
terminology
that it's arbitrary that we go from left to right and we fill the levels. So
then how do you, like, when does it stop? Like, how do you know when you...
So here's another way to think of it. So pretend I have this framework for a binary tree. And here's the first guy, and then second, third, fourth, fifth, sixth, seventh, and I just go across like that. Right? It's complete if there are no gaps, like I didn't skip one. So I start at the top, and then I fill from left to right. And as long as I'm filling like that, not leaving any gaps from left to right, it's a complete binary tree.
And so then because that's the final...
That's the depth, that's the deepest part of the tree,
right,
I can leave that open. So there's nothing deeper, nothing in here.
So then you only technically need like one node at depth n if it's all the way on the left side?
Yep, exactly.
Okay.
Exactly.
Okay.
Yep.
And so the idea of completeness is almost more applicable when you already have that framework.
Yeah, exactly. It's sort of like you've already got the framework and you're just filling it in.
Okay.
Why do we care about complete binary trees? Because they're the most efficient binary arrangement, if you will, of the data. We don't like this tree a whole lot. It's a binary tree, but we don't like it because it's really deep. It doesn't need to be that deep to hold all these nodes. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 nodes in here. And the tree is 1, 2, 3, 4, 5, 6 deep. How many pieces of information can I fit in a tree that's 6 deep?
A lot. 2 to 6. No. +1.
Maybe +1, yeah. A lot. And certainly a hell of a lot more than 13. So that's why we have this extra notion of a complete binary tree, because an incomplete binary tree is potentially very inefficient. And so what we'll have is we'll be building these binary trees, and then we'll talk about, I think in the last couple of weeks of the semester, we'll talk about AVL trees, which are binary trees that you build, and every once in a while the tree gets too deep, and what you can do is do these massive rotations. You can rebuild the tree and sort of make it less deep, closer to a complete binary tree, so it's more efficient for searching. Searching, you want to minimize depth for searching. That's when you're getting the most bang for the buck.
Is the data always conducive to building?
It's not always. In AVL trees, in fact, it's an open question in mathematics/computer science as to whether you can always balance an AVL tree with a particular set of data.
Balance and make
Make it a complete binary tree. Yeah. Well, balance is close to complete anyway. It's not quite complete. The openings in that bottom level might be anywhere.
Oh, gotcha.
But it's an open question as to whether you can always, for arbitrary data, as you're pushing it into this AVL tree, it's an open question as to whether you can keep it balanced.
So all leaves have depth.
Exactly, yeah, exactly. We'll talk more next time about tree traversals. There's a really cool thing in David's book. Let me just leave this with you to show you that there's more than one way to think about particular ideas. No, I want to go here and here. So you remember our infix calculator, no doubt.
Yeah, it took like 20 minutes. I hardly remember.
Exactly, yeah. Okay, check this out. So here's an expression, an infix expression represented in a binary tree. Let me talk about what's called in-order tree traversal. The in-order tree traversal says print the left tree, then print the root, then print the right tree. And you do it recursively. So I start at the root and I say, okay, print the left tree. So I go here and I say, oh, okay, print the left tree. So I go here and say, oh, there is no left tree. So I'm going to print out the root. And then I'm going to print the right. Oh, there's no right, so I'm done. Now I'm going to go back up here because I'm still printing the left tree. And I'm going to print out root, which is plus. And then I'm still printing this tree, so now I print the right. So I'm going to print out 2. Now I'm done with this tree. I'm going to move back up here and I'm going to print out the root. And now I'm going to print out the right tree. Well, how do I print out the right tree? Well, I print the left tree. And there's no left tree here, so I print out the root, and then I print out the right tree. Then I go back up here and I print the root, and then I print the right tree, which is this guy. And now I'm done with the right tree, and I'm done with the tree. And what have I just done?
1 plus 2 times.
I printed out that infix expression. What's super, super cool is you can do postfix just by printing the tree out in left tree, right tree node order. So I'm going to print the left tree, I'm going to print the left tree, I print it. Now I'm going to print the right tree, print it. Now I'm going to print the node. So infix, postfix, prefix are all just different tree traversals for these expressions. Very cool. Okay, I'll leave you with that.
So would pre be node left, right?
Pre would be node left, right, yes.
You also just like put in parentheses between subtrees.